Good morning, linear algebra class. Today we are going to talk about row, column, and null spaces of a vector or of a matrix, sorry. If you have any questions from section 4.6 or actually anything 4.4 to 4.6, go ahead and shoot me an email. I'll be glad to try to answer by email. And if that does not work or that doesn't answer your question, then we can do a short Zoom session and figure out what you have questions about. Remember that you have a quiz on Tuesday over 4.4 to 4.6. I'm going to give you your joke of the day. Fairly appropriate for the time that we are in. And then let's get started on our lesson. We are talking about row space, column space, and null space. First thing we want to do is define what row vectors and column vectors are. So if we have a matrix A with the typical entries A11, A12 in the first row, A21, A22, etc. If you take the rows of that matrix and write those as vectors, those are called the row vectors. And if you take the columns respectively, A11 to AM1, A12 to AM2, etc., those are called the column vectors. Row vectors have n entries, so those are elements in Rn, and column vectors have m entries, so those vectors would be in Rm. These notes are posted on Blackboard, so if you want to look at those, print those out, or just use those as notes, you can do that, but you can also pause this so that you have time to write. Okay, our first definition is the row space, column space, and null space of a matrix. So if A is an m by n matrix, then the subspace spanned by the row vectors of A is called the row space. The subspace spanned by the columns of A is called the column space. And the solution space is the space of solutions to the homogeneous system AX equals 0, which we've already defined that, but we wanted to redefine it in this context. That's called the null space of A. So the set of solutions to AX equals 0 is called the null space. These are the notations that we would use for those. Just each word with the A in parentheses. Given these definitions, a system AX equal B can be written as, here's our matrix A, our variables x1 to xn as a column, and then our constant matrix B1 to Bn. And we talked about this way back in chapter, I think it was 2, how we can take that system and write it as a linear combination of the columns of A. So x1 times column 1 gives us the first column of the system, x2 times column 2, etc. That will, this side over here gives us the system with coefficients and variables, and then B is the constant matrix, or constant vector. Okay, that system that we just looked at is going to have a system, a solution if B is in the span of the column vectors. So if I can form a linear combination of those basis vector, those column vectors, and find variable values that are coefficients of those vectors that give me B, then we say that B is in the column space of A. And there's a theorem that says that. So if you have a system of linear equations, it's consistent if and only if B is in the column space of A. So we're going to go both directions here. If B is in the column space of A, AX equal B is consistent. If AX equal B is consistent, then B is in the column space of A. All right, let's look at an example. Here's a matrix A. It has rows 1, 1, 2, -1, -2, 3, and 3, -7, 4. Our constant matrix is 8, 1, 10. And we want to determine if 8, 1, 10 is in the column space of A. So in other words, can B be written as a linear combination of the columns of A? So I broke it down in here and wrote AX equal B as a linear combination of the basis vector of the column vectors. X1 times the first column, X2 times the second column, and X3 times the third column, and set it equal to 8, 1, 10. If you write that system without variables, put it in reduced row echelon form, this is the matrix that results. So indeed, there is a solution. We have the identity matrix on the left-hand side, and we have 3, 1, 2 on the right side. That means that we can take 3, 1, 2, we can write 3 times column 1, 1 times column 2, plus 2 times column 3, and that will give us B. So B is in the column space of A. Now, what does it look like if B is not in the column space of A? Then we would get some matrix up over here that is not the identity matrix. So after we put that in reduced row echelon form, we would not have the identity matrix. So I'm sure you'll have some homework that looks like that. You need to determine if a vector or a matrix is in the column space of A, and that's how you would do it. Write a system, put it in reduced row echelon form, and then see if you actually get a solution. All right, now we are going to move on to finding bases for these spaces, the row space, the column space, and the null space. We want to find out how to find a basis for those. We're going to start by looking at solutions to a system of equations in different pieces. So if x0 is any solution to ax equals b, so it doesn't matter what it is, any solution. If s equal v1 to vk, a set of vectors, is a basis for the null space, then every solution to ax equal b can be written in this format. X is an arbitrary solution. X0 is the solution to ax equal b that we wrote up here. And this is a linear combination of our null space basis vectors. If that is true, then for any choices of scalar, this vector x, written in this form, is called a solution to ax equal b. So x0 is a solution to ax equal b. This is a solution to ax equals 0. Because v1, v2 through vk are basis vectors for the null space. If I write a linear combination of those, that has to also be a solution to ax equals 0. All right, here's the proof, and this is rather lengthy, and it's not in the book, but I wanted you to see this. We're going to let x0 be a fixed solution to ax equal b, just like we had before. Let x be an arbitrary solution to ax equal b, so that would be another solution. And let s equal v1 to vk, so these are the basis vectors for the null space of A. We need to show that every solution ax equal b can be written in this form. And to do that, we're going to start by saying ax0 equals b, because x0 is a solution to the system, and ax equal b. Those are both, x and x0 are both solutions to the system ax equals b. If we subtract those, ax minus ax0, we get b for ax, b for ax0, and b minus b is 0. But we can also take ax minus ax equals 0, use a reverse distribution process, and find out that that's a times x minus x0. We know that that's equal to 0, which tells us that x minus x0 has to be a solution to ax equals 0. Now, since s equals V1 to Vk is our basis for the null space of A. X minus x0 being a solution has to be able to be written as a linear combination of those vectors for some scalars C1 to Ck. Then if we add x0 to that, we show that every solution x, an arbitrary solution x for the system Ax equal b, can be written as x0, the specific solution, plus a linear combination of our null space basis vectors. Now we need to do the converse. So we need to show that for any scalar C1 to Ck, this solution works for Ax equals b. So we start with A times x. We want to find out if that is equal to b. X is this expression, x0 plus a linear combination of null space basis vectors. I distributed the A across each of those pieces. Ax0 is b because x0 is the solution to the system. And then I used the associative property to move C1 or each constant, each scalar out in front, each coefficient, and I have A times each vector. Each of those vectors is in the basis for Ax equals 0, so they have to give you a solution of 0. So we get b plus however many zeros, therefore x is a solution to Ax equals b. So there's the proof of that theorem. Now here's what it's going to look like when we use that. X0 is called a particular solution to Ax equals b. The expression x0 plus that linear combination is called a general solution to Ax equal b, and just the linear combination of basis vectors v1 to vk is called the general solution to Ax equals 0. And here I've diagrammed it out. I wrote out that expression. X0 is the particular solution. C1 V1 to CK VK is the general solution to Ax equals 0. And if you put those together, you get the general solution to Ax equals b. When we're looking at an actual example for this, the particular solution x0 will come from the constant matrix B in your system. All right, let's look at an actual example here. So we have x0 is a particular solution. It should be -1, 2, 4, -3. That's a solution to Ax equal b. And then we have a general solution to Ax equals 0. Notice that this is in parameter form. We have two parameters, r and s, and then x1 and x2 are linear combinations of those. So it says find a general solution for Ax equals 0 and also for Ax equal b in vector form. So for Ax equals 0, all I need is to write x1, x2, x3, and x4 as a linear combination of basis vectors. And this is like a problem that we did 2 sections ago in 4.5, where we're writing the -3r plus 4s, r minus s, r, and s as a linear combination of vectors. So r would be taken times -3, 1, 1, 0, and s would be taken times 4, -1, 0, 1. V1 and V2 here are basis vectors for the null space of A. And then to find the general solution for Ax equal b, the only thing that we need to add to that is to take our particular solution, -1, 2, 4, that should be -3. Plus the linear combination that we used in the step above. So this is how you would write a general solution for Ax equals 0 and one for Ax equal b. The particular solution, if you're asked that, is what's given up here. Okay, couple theorems about what happens to basis vectors or rows and columns if we perform elementary row operations. If you perform elementary row operations on a matrix, it does not change the null space of a matrix. That's the first theorem. And the second one is that the elementary row operations don't change the row space. So I can perform row operations on a matrix and it doesn't change the row or the null space of that matrix. The same thing does not hold for columns. If you perform row operations on a matrix, it does change, or I should say it can change, the column space of a matrix. So we'll look at a different way to find basis vectors for a column space. Our goal now is to find basis vectors for the row and column spaces of a matrix. So here's a theorem that tells us how to do that. If we have a matrix R that's in row echelon form, reduced row echelon form is fine, then the row vectors with leading ones form a basis for the row space of that matrix, and the column vectors containing leading ones of the row vectors, so those same leading ones we had, form a basis for the column space of R. So we can take any matrix, put it in row echelon or reduced row echelon form, and those leading ones will tell us which vectors to use for bases for row spaces and column spaces respectively. So here's an example of doing that. Find the basis for the row and column spaces of R. This is a matrix that is in row echelon form. Actually, it's reduced row echelon form, but it doesn't really matter. The leading ones here and here. So those tell me which basis vectors I want to use for the row and column space. For the row space, I'm going to use row 1 and row 2 because that's where the leading ones are. That gives me a basis for the row space of R being the first and second rows of that matrix. Those leading ones are in the first and second columns of R, so I'm going to use the first column and the second column as a basis for the column space of R. Now this matrix R up here came from this matrix A. And since row operations don't change the row space of a matrix, we had that in the theorem at the top of the page, I can use the first two rows of R, and that will form a basis for the row space of A as well as R. I'm going to say that one more time. Row operations don't change the row space of a matrix. So the same two basis vectors that I used for the row space of R can be used for the row space of A. All right, finding a basis for the column space of matrix A that's not in row echelon form takes a little bit more work. And what this theorem tells us is, let me get that up just a little bit. If A and B are row equivalent matrices, so they are the same system, but they have had elementary row operations performed on them. A given set of column vectors of A is linearly independent if and only if the corresponding column vectors of B are linearly independent. So rather than using exact vectors, what we're doing is using corresponding vectors. The vectors in a row echelon matrix will indicate which columns or rows we need to, columns we need to use in the original matrix. B says if a given set of column vectors of A forms a basis for the column space of A, then the corresponding column vectors of B form a basis for the column space of B. So this is an indicator, not an exact vector. If you think of B as R in this case, it's going to help a lot. All right, here's an example of that. Here's our matrix A that we had on the last page, and here's our matrix R. A basis for the column space of A will use the vectors from the columns of A. So we're going to use columns of this matrix that correspond to the column vectors used for the basis for the column space of R. For the column space of R, we use the first two. which means we're going to go over to matrix A, and those same two vectors, columns 1 and columns 2, will give us a basis for the column space of A. So if you're dealing with rows, you can use the same rows basis vectors for the row space of A and the row space of R. For columns, you've got these for the column space of R. If you want a basis for the column space of A, you're going to use the same corresponding vectors in matrix A. All right, here's another example just to demonstrate this a little more. Our matrix A, 1, 4, 5, 2, 2, 1, 3, 0, and negative 1, 3, 2, 2. And here's the reduced row echelon form of that, found from the calculator. And it says to find bases for the row and column spaces of R and A. So we want 4 different bases here. Row space of R, column space of R, row space of A, and column space of A. We have leading ones in the first row, first column, and second row, second column. That means we'll be focusing on those to find our basis vectors. For the row space of R, we will use the first row and the second row, since those are the rows that contain leading ones. For the column space of R, we will use the first column and the second column. That's where the leading ones are. When we go for the row space of A, we can use exactly the same vectors that we use for the row space of R, because row operations do not change the row space of a matrix. So these two are going to be exactly the same. For the column space of A, we need columns of A that correspond to what we used in R. Since we used the first and second columns of R here, we're going to use the first and second columns of A to form a basis for the column space of A. All right, the last thing we want to do is we want to see if we can find basis vectors for the row space of A that are actually rows of A and not R. And we're going to pull a little trick here. It's not hard. We're going to look at A transpose. If we write A transpose, so this is the transpose of the matrix that we had at the top of the page, then the row space of A is the same as the column space of A transpose. I found the reduced row echelon form of A transpose, and this would indicate that we want to use columns 1 and 2 of A transpose as a basis for the column space of R. That translates to columns 1 and 2 for a basis for the column space of A transpose, which means now we can take the basis for the row space of A being the first 2 rows of A, since that corresponds to the columns of A transpose. All right. That's it for notes from section 4.7. It's a little bit long, and I just thought it might be easier to do it this way so that you can do it on your own time, sleep in a little bit maybe, stop the video when you need to so that you can write or add comments to notes that you've printed out. Your homework is on Blackboard. Remember again that you have a quiz on Tuesday over 4.4 to 4.6. And I hope you have a good weekend, and I will see you back at normal time, 8 o'clock on Tuesday for class.